Hi, this is Group 72, and our project is neural network prediction of the inverted pendulum on a part. Inverted pendulum system is a simple cart with a pendulum attached to it, and we use a forcing function to move this part. And we are gonna show that neural network can be used to predict this system of state variable as a very nonlinear and unstable system as a black box or a gray box model, and we want to show it has the power to uh, predict this variable. What are the IP variables? They are cars position and velocity, and pendulum's angle and angular velocity. For data source, we used these two ODEs, and we generated more than 20 million data. We had some fixed parameters, as you can see here, and we had some input and output variable. The inputs are forcing function, angle and angular velocity, and initial position and velocity. We used three different models for this purpose. At first, the MLP, which had five input in input layer at time is equal to 0 and four inputs after 1 millisecond. It has six hidden layers, each has 100 neurons. And we use the whole data set to predict this model. And you can see the simple of architecture here. The MLP model was very computationally expensive, so we introduced a naive neural network. Here, the time is another input, and we just have the position and angle as the output. We still have six hidden layer, but different neurons, and the other difference is the initial conditions here. Some of them are fixed, and we just change the initial angle and forcing function. And the final model is physics-informed neural network. Uh, Again, same input and output, but three hidden layer with 13 neurons each. The main difference of this model with others is the loss function that can be calculated by adding the MSE of initial conditions, I mean, initial angular position and their derivatives, and the MSE of the ODE, and MSE on a very sparse data, for example, 7 data points. And also here, these parameters can take any values, and the forcing function can be any variable that you want. So it makes this very more interesting. So about the performance, the MLP didn't perform well. Even we utilized the whole data set to train it. The main reason for this was the data in the time set, I mean, in 1 millisecond wasn't dense enough. And if we want to get a better performance, we should use more than thousands of this data set, which would be very expensive, computationally expensive. So it's not very reasonable. But hopefully the naive neural network perform much better with much less data set. Here is the model with 3 neurons and 100 neurons, and you can see that it could predict well. And the best one was the physics informed model. Even with 7 data points, it predicted well, even in the area that we didn't provided any data, for example, here or over here. In the naive neural network, we had underfitting issue when we have an interpolation of the forcing function. Here, 32 neurons, it didn't go well, but in 100 neurons, it did well, as you can see. Uh, but when we have interpolation of the initial angle, it was different, and we have overfitting issues in 100 neurons version. Uh, in this in this condition, it can't be very well on the X prediction, but for the angle, it would perform better with 32 neurons. And finally, as I mentioned, the best performance was achieved by the pin model. For example, here we had a variable forcing function, cosine function, and after a few steps, it would perform well. It is the final version, which predicted well, even in this area. That was very interesting, and because we didn't have any data here. Uh, Dan has prior experience attempting to control a card pendulum system in a control course with PID controller, and other didn't have any experience with this project. Thank you.